What if the biggest barrier to true artificial intelligence isn't a lack of data or computing power, but a fundamental misunderstanding of how the world moves? We often assume that if we just feed enough information into a model, it will naturally learn the rules of physics. But new research suggests the opposite might be true, that our most advanced AI systems are accidentally ignoring the very laws of nature they need to master. Welcome to a deep dive into the future of intelligent machines. Today, we are exploring a pivotal shift in how we build artificial intelligence, moving from simple pattern recognition to something far more profound: physics-grounded reasoning. You are about to discover why the next generation of AI isn't just about predicting the future, but about understanding the physical constraints that govern it. Stay until the end, because the findings we discuss today reveal a hidden flaw in current technology that could be holding back the entire field of robotics and quantum computing. For decades, the race toward artificial general intelligence has been defined by a singular goal: creating models that can see, reason, and act just like humans. We have built systems that can diagnose diseases, drive cars, and even write code. Yet, beneath this rapid progress, a quiet problem has been brewing. As we delegate more complex tasks to AI, from coding software to managing quantum computers, we risk accumulating what researchers call knowledge debt. This isn't about money. It is the cognitive cost of relying on tools we don't fully understand. When we use AI to solve problems without grasping the underlying principles, we create a fragile foundation. The problem is that many of today's world models, no how sophisticated, are treating the universe as a collection of static images rather a dynamic, evolving reality. They excel at recognizing patterns in the short term, but stumble when asked to plan for the long horizon. This disconnect means that while our machines are becoming incredibly fast and accurate in isolated tasks, they often fail to generalize when faced the unpredictable chaos of the real world. So, what have researchers actually found? In a series of groundbreaking studies released in July 2026, a team of scientists uncovered a startling diagnosis of why these long-horizon models fail. They discovered that many advanced AI systems are suffering from what they call a kinematic fallback. Imagine watching a movie of a bouncing ball. A kinematic model can perfectly predict the arc of the ball based on its past motion. It sees the pattern. However, a dynamic model understands why the ball bounces, understanding gravity, air resistance, and the elasticity of the ground. The research reveals that our current AI, despite its complexity, often relies on these surface-level kinematic patterns rather than deep dynamic rules. In one study focusing on long-horizon planning, models that relied on kinematic consistency showed an error rate 180 times higher than those grounded in actual physical dynamics. It is as if the AI is memorizing the choreography of a dance without understanding the music or the rhythm driving the movement. But the story does end with failure. It begins with a solution. The same research introduces new frameworks like RIN-World 4D and ONS that are changing the game. RIN-World 4D proposes a unified approach that synchronizes appearance, geometry, and motion into a single four-dimensional representation. Instead of processing video, depth, and movement separately, this model weaves them together, allowing robots to achieve a level of dexterity that was previously impossible. It eliminates the computational bottleneck of step-by-step inference, enabling real-time, closed-loop control. Imagine a robot hand that doesn't just see an object, but instantly understands its weight, its texture, and how it will move if pushed, all in a fraction of a second. Similarly, the ONS framework applies this physics-grounded reasoning to the microscopic world of quantum computing. Diagnosing faults in cryogenic infrastructure is notoriously difficult, often requiring massive datasets of labeled errors. Yet ONS, a multi-agent LLM, achieved accuracy nearly identical to traditional supervised machine learning methods using zero-shot reasoning. It did not need millions of labeled examples. It used logic and self-consistency to deduce the answer. This is a paradigm shift. It moves us away from the idea that AI needs endless data to learn. Instead, it shows that if we embed the laws of physics directly into the architecture of the AI, we can create systems that reason from first principles, much like a human scientist would. This approach also extends to how we work with AI in our daily lives. New findings suggest that while AI can boost productivity, unchecked delegation leads to a decline in human comprehension. The most effective future lies not in replacing human judgment, but in designing systems where AI and human learning grow together, preventing the atrophy of our own skills. The implications of these discoveries are profound for both science and society. For the field of robotics, this marks the end of the era where robots operate in a closed world of pre-programmed rules. We are moving toward open-world agents that can actively verify their own hypotheses and adapt to uncertainty. This means robots operating in complex environments, from disaster zones to outer space, will be more robust and less prone to silent failures. In the realm of quantum technology, the success of physics-grounded AI suggests a path towards self-healing infrastructure that can monitor and fix itself without human intervention, overcoming the scarcity of labeled data that has long plagued the industry. Perhaps most importantly, this shift challenges our cultural relationship with technology. We are learning that efficiency cannot come at the cost of understanding. By identity,